Section 2.3 Functions. Definition. Let A and B be non-empty sets. A function from a set A to B, denoted this way, is an assignment that maps each element of A to exactly one element of B. We write f of A equals B if B is the unique element of B assigned by the function f to the element A of the set A. Functions are sometimes called mappings or transformations. And here we have a function from the set of these four students to the set of all grades from A to F. So, Carlota Rodriguez has an A, Sandeep Petal has a B, and so on. The definition of a function can be rephrased as one of a relation that meets certain requirements. A relation is just a subset of the Cartesian product of A and B, the set of all pairs. A relation is a function if it meets these two requirements. For every x, if x belongs to A, then there is a y from B, and such that the pair xy is in the relation F. And the second requirement is for every x, y1 and y2, if xy1 belongs to F and xy2 belongs to F, then y1 is equal to y2. That is, the second requirement is that there is only one pair that starts with x for any x from the set A. Given a function f from the set A to the set B, we say f maps A to B, or f is a mapping from A to B. A is called the domain of f, B is called the codomain of f. If f of A is equal to B, then B is called the image of A under F, and A is called a preimage of B. Let's mention here that B can have different preimages, not just one. Many different preimages. The range of F is the set of all images of points in A under F. We denote the range by f of A. Two functions are equal when they have the same domain, the same codomain, and map each element from the domain to the same element of the codomain. Functions may be specified in different ways. An explicit statement of the assignment, for example, the students and grade, the students and grades example, with a formula f of x equals x plus 1, for example, with a computer program, a Java program that when given an integer n produces the nth Fibonacci number. In this example, we consider this map, which is denoted with f. What is f of A? F of A is Z. The image of D. The image of D is Z. The domain of F is the set A. The codomain of F is the set B, which consists of x, y, and z. And the preimage of Y is B. F of A, the image of A, this is Y and Z. the set of all images yz. The preimage of z consists of all elements of A that maps to Z. So A, C, D. The preimage of Z consists of this subset of A. If S is a subset of A, then the image of S is the set of all images F of S such that S belongs to S. The image of ABC is ABC YZ, the set YZ. The image of the set CD is just the subset Z of B. Definition: a function f is said to be one-to-one or injective if and only if f of A equals f of B implies that A is equal to B for all A and B from the domain of F. Such a function is called also injection. In other words, F is one-to-one if any two different elements from A have different images under the function. A function f from A to B is called onto or surjective if and only for every element B in B there is an element A in A such that f of A is equal to B. A function f is called a surjection if it is onto. In other words, f is surjective if f of the set A is equal to the set B, the codomain. A function f from A to B is one-to-one correspondence or bijection if it is both one-to-one and onto. Suppose that f is a function from the set A to the set B. To show that f is injective, show that if f of x is equal to f of y for arbitrary x and y in A, then x is equal to y. To show that f is not injective, find particular elements x and y in A such that they are different, but f of x is equal to f of y. To show that f is surjective, consider an arbitrary element y in B and find an element x in A such that f of x is equal to y. To show that f is not surjective, find a particular y in B such that f of x is different from y for all x in A. In example 1, we have a function f from the set ABCD to the set 1, 2, 3, and it is defined explicitly. Is this function onto? And the answer is yes, because each element from the codomain 1, 2, 3 is an image. In example 2, the function f is defined with a formula x squared, f of x is x squared, and it is from the set of integers to the set of integers, from z to z. Is this function onto? The answer is no, because, for example, -1 is not an image of any integer under f. Definition of inverse function. Let f be a bijection from A to B, then the inverse of f, denoted this way, is the function from B to A, defined as f, the inverse of f of y is x if and only if f of x is y. No inverse exists unless f is a bijection. So we simply reverse the arrows to find the inverse function. In this example, it is clear that f is a bijection from A to B, so it has an inverse function, and the inverse function of f sends B to A, and we simply reverse the arrows. This arrow here for f points from D to V, and here we have an arrow pointing from V to D. And we do this for each of these arrows to get the diagram of the inverse function of f. In this example, f is the function from ABC to 1, 2, 3, defined explicitly with these equations. Is f invertible, and if so, what is its inverse? It is clear that f is 1 to 1 and 1 to 2, so it is invertible. And then f to the negative 1, the inverse function of f at 1, is what? C, because f of c is 1. The inverse function of f of at 2 is a, because f of a is 2, and the inverse function of f at 3 has value b, because f of b is 3. In this example, we have a function f from z to z defined with this equation, f of x equals x plus 1 for any x in z. Is it invertible? And if so, what is its inverse? This function is 1 to 1 and 1 to 2, because it is a bijection, it has an inverse. F of x adds 1 to each integer, the inverse function will subtract 1 from each integer. In this example, f is a function from the real numbers to the real numbers, and it is defined with this equation, f of x is equal to x squared for any real x. Is f invertible, and if so, what is its inverse? The function f is not invertible because it is not 1 to 1. For example, f of negative 2 is equal to f of 2, and negative 2 is different from 2. So it is not injective, and therefore it is not a bijection. For that reason, f does not have an inverse function. Definition of a composition of two functions. Let f be a function from B to C, and g be a function from A to B. A, B, C are three sets. The composition of f with g, denoted this way, is the function from A to C, defined this way. The composition at x is equal to f of g of x. So at A, g is defined because A is in the domain of g. We apply g, and to the result, which is g of A, we apply f. We arrive at this point, so the composition function at A has value fg of A. Here, G is given with its digraph, F is given with its digraph. Find the digraph of the composition function, fg. What is fg of A? First we apply G, we go here, then we apply F, which means that the composition of F and G sends A to J. And we continue like that. B, apply G, you go here, then apply F, you go here. So the composition is sends B to H, B to H. And we fill out, we draw the remaining arrows like. In these examples, F and G are functions from R to R. F is defined with this formula and G is defined with this formula for any real number x. Then fg of x is apply first G and then F. We get 2x plus 1 squared. Gf is what? Apply first F, you get x squared here, and then apply G, 2x squared plus 1. In this example, G is the function from the set ABC to itself, defined explicitly like this, and F is the function from the set ABC to the set 1, 2, 3, also defined explicitly with these equations. What is the composition of F and G? And what is the composition of G and F? The composition of F and G is defined using the definition. So apply first G to A. G sends A to B. So we have F of B, and F of B is 2. So the composition of F and G sends A to 2. And similarly, it sends B to 1 and C to 3. The composition of G and F is not defined because the range of F is not in the domain of G. The range of F is 1, 2, 3, and it is not in the domain of G. Example, let F and G be functions from the set of integers to the set of integers defined by these two equations. For any integer x, f of x is 2x plus 3, and g of x is 3x plus 2. What is the composition of f and g, and what is the composition of g and f? We apply the definition. G of x is 3x plus 2, and f of 3x plus 2 is 2 times this thing plus 3. Apply the distributive law and simplify, you get 6x plus 7. 2 times 2 plus 3 is 7. G composed with f at x is this by definition, and f of x is 2x plus 3. G of 2x plus 3 is 3 times 2x plus 3 plus 2. And we get 6x plus 9 plus 2. 9 plus 2 is 11. And we see that these two functions are different because the first function sends x to 6x plus 7, while the second function sends x to 6x plus 11. Let f be a function from a set A to a set B. The graph of the function f is the set of all ordered pairs such that A is in A and f of A is equal to B. It is ordered pairs A, f of A. This is the graph of the function f of n equals to n plus 1 from z to z. And this is the graph of the function f of x equals x squared, which is by definition from z to z. The following two functions are important for discrete mathematics. For any real number x, the floor function denoted f of x equals, so this is how we denote the floor function, is the largest integer less than or equal to x. The ceiling function, defined this way, denoted this way, is the smallest integer greater than or equal to x. For example, the ceiling of 3.5 is 4, and the floor of 3.5 is 3. The ceiling of negative 1.5 is negative 1, because this is negative 1 is greater than negative 1.5 and is the smallest integer with this property. And the floor of negative 1.5 is negative 2. This in A here we have the graph of the floor function. The floor of 1 is 1. So this point is in the graph. Well, this point here is hollow. It is not on the graph. But any real number less than 1 and bigger or equal to 0 is mapped to itself. It's mapped to 0 here. So this line is in the graph of the floor, and this point is filled, so it is on the graph. So in each line segment, the left-hand side is on the graph, the right-hand side is not on the graph. For the ceiling function, in any line segment, the right end is on the graph, the left end is not on the graph. In this table, we have some useful properties of the floor and the ceiling functions. Here, n is an integer and x is a real number. The floor of x is n if and only if n is less than or equal to x and strictly less than n plus 1. The ceiling of x is n if and only if n minus 1 is less than x and x is less than or equal to n. And we continue with the remaining properties. Each of these properties needs a proof, and we give an illustration on the next page. In this example, we'll prove this equality, which involves the floor function. For any real number x, the floor of 2x is equal to the floor of x plus the floor of x plus 1/2. To prove, we consider x in this form: n plus epsilon, where n is an integer and epsilon is a number between 0 and 1, strictly less than 1. It is clear that any x can be written like that. And we consider two cases for epsilon: less than 1/2, or in the other case, epsilon is greater than 1/2, so it will be from 1/2 to 1 in the second case. Since epsilon is less than 1/2, when we multiply this equality by 2, we'll get this, and here the floor of 2x is 2n, because 2 epsilon is strictly less than 1 and greater than or equal to 0, because epsilon is less than 1/2. 2 epsilon is less than 1. So the left-hand side of our equality is just 2n. What is the right-hand side? The floor of x plus 1/2 is n, since x plus 1/2 is equal to n plus 1/2 plus epsilon, and this number is between 0 and 1, strictly less than 1. So the floor of x plus 1/2 is n, and the floor of x is also n, so the right-hand side is n plus n, 2n. So the left-hand side is 2n and the right-hand side is 2n. They are equal. We have equality in case 1. In case 2, 2x is 2n plus 2 epsilon. 2 epsilon is bigger than 1 in this case. So 2 epsilon plus 2 epsilon minus 1 will be between 0 and 1, strictly less than 1. Which means that the floor of 2x will be 2n plus 1. So we know the value of the left-hand side, 2n plus 1. Compute the value of the right-hand side. X plus 1/2 is this. And we can write it as n plus 1 plus epsilon minus 1/2. Just subtract 1 from this expression in the parentheses. It becomes epsilon minus 1/2. Because epsilon minus 1/2 is between 0 and 1 and less than 1, the floor of this is just n plus 1. The floor of x is n. The floor of x plus 1/2 is n plus 1. And we get 2n plus 1 as value of the right-hand side, which is the same as the value of the left-hand side. So both are equal in this case 2 as well. And this completes the proof. The definition of factorial function is a function from n to z plus, denoted this way: f of n is n with exclamation mark. We read this as n factorial. Here n, it is defined this way: f of n is 1 times 2 times and so on, n minus 1 times n. if n is bigger than 0, and f of 0 is just 1. These are some values of n factorial. 6 factorial is 720, and 20 factorial is this big number.